welcome back. So today we are going to talk about the MATLAB model development for digital voltage mode control. This is the continuation of the previous lecture. In this lecture we will continue using our difference equation for digital control implementation, and I want to summarize what are the steps overall for overall digital voltage mode control implementation, and I want to show few case studies. So here this is the block diagram of the digital voltage mode control that we have learned, and we have already discussed A to D converter. The first requirement is a sampling block. This is a sampler. Then we can use a quantizer block, and we can use also a delay. Okay. So in order to start with the sampling block, the basic block is a zero order hold that we have learned, and this zero order hold is used to take the sample. But this hold process, if you go to the zero order hold, you need to provide the sampling time. But if you provide sampling time, it will sample with respect to the simulation time, and that with the capital T. That means it will start from the start of the simulation, and after every T time it will sample. But we want to customize the edge as well as we want to use an event based clock. So we need event trigger A to D converter, and this is the block that we have discussed. Inside the event trigger we have a zero order hold block as well as the enable block as well as the event block. So whenever this edge come, the rising edge come, then only it take the sample. Okay, so that means this is now the event clock, event trigger A to D converter. Then next part is the quantization. So we can add a quantizer and we can add a delay, and delay we can add. I will go to the MATLAB and show. So let us go to the MATLAB, because if you go side by side it will be easy. So this is the block I am talking about, event trigger A to D converter, and if you go inside that block, you can see inside this block there is a zero order hold. Since you are using inside an enable and trigger, so there is no need to specify sample time. You can use the by default zero order hold which is there in the library. But whenever this enable goes high, then only it will sample, and this trigger will actually enable will enable this block. ADC will be enabled. If it is 0, the ADC will never be enabled. And then when it is enabled, then we have to send the trigger pulse when it will sample. And in this block, if you go inside, it has a by default hold circuit. That means it is like a register where it will store. We need to initialize the register, V0 initialization. Okay, so it is possible. Then if you want to incorporate a quantization, so let us first run without quantization, without this delay. So what will happen if we go to this MATLAB block, and if we run it, there we are not using any quantization. So let us see if we use a quantization block, and this is with some delay. Now we are going to use this quantization block. That means let us use a quantizer. So we can go to the library and we can use a quantizer here. So let us see a quantizer. So this is a quantizer, and if you so we can just use this quantizer. Now the quantizer interval, it's like a voltage interval. So we need to provide, maybe we can give 10 millivolt, 10 millivolt, or maybe 10 millivolt. So you can provide a 10 millivolt quantizer, and we want to see what happened after this quantization block. So the earlier simulation there was no quantization. Now we have added a quantization, and see what happened. So now you can see, because this is the quantized data, you can see that because of the quantization level, actually it is unable to differentiate the close values. Okay, so that's why, and quantization induce some instability is coming, but once it is, you can ensure the dynamically it is stable, then here the quantization level is reached and there is no stability problem. But due to quantization there can be sort of instability, and we will discuss also in that analysis case. Now if you reduce this quantization level, that means if you reduce to, let us say, 1 millivolt, then you can actually improve this response. That means you can make you can somewhat improve the stability status. So you can see now the effect is substantially reduced. It is there, but it is substantially reduced, So, that means as if and the steady state also there is a small kind of after long time, like then only this effect is gone. But due to this quantization effect, you will have some slow scale oscillation, okay, and we will talk about this quantization effect. This may lead to limit cycle oscillation, or in fact it may lead to high periodic behavior. But if we do not incorporate for the time being this quantization effect, then we can simply discard this block and you can continue with our earlier block, okay. So, that means we can incorporate this block, and let us go to our presentation. Okay, yeah. So, that means we can add this quantization block. We can add delay, that we have already discussed, that how to delay the clock. So, everything can, that you can add a physically, you can add a delay in this MATLAB. So, if you go, you can use a delay block, there will be a transport delay. So, you can simply take a transport delay here, okay, and here you can specify what is the delay amount. So, these are the possibility. I am not going all this, but I am just showing these are the, you can of course make the simulation more realistic, okay. So, now in the MATLAB model we have this buck converter power stage, and this will go to, so we have to close the loop, and this is our ADC block. Then next part we need an adder circuit. So, this is just a simple adder, okay. This is our sample voltage, then it is basically a subtractor, then we need compensator P, Pi, PID, and we have discussed this compensator can be realized using clock driven, that we have discussed in the previous class. And for this is for the PID controller. So, earlier one is the PI controller. So, any controller that we can implement. So, this block, although it looks like a block, but in MATLAB it is not a block, it is basically a difference equation if you go inside. So, this is the whole realization of this. So, this part you can consider your transfer function, that is equivalent to the transfer function, and that is realized using difference equation using a clock driven operation. Next is that once it is done, then we can use a repeating sequence for sawtooth waveform, but you can also use a staircase type repeating sequence, that will give an feeling of quantized staircase, because if you go to a digital platform, this staircase will be generated inside a digital controller, and will be actually we have discussed this for different digital like a DPWM architecture. So, you can use a simply counter based DPWM to implement this, or there are other architecture like delay line DPWM or hybrid DPWM, but you can get this kind of sequence with staircase effect. Then after this block you have to use a comparator, this is a comparator, and then we can use a sawtooth, that means the latch circuit. So, this is a that is the main pulse width modulation, trailing edge modulation block, and then you can actually use the overall buck converter model. So, this is the overall digital voltage mode controller model that we have discussed. And if you zoom this portion, that means if you zoom this portion, we have discussed, this is a power stage, okay, where we have switch node voltage, inductor dynamics, then capacitor dynamics, and then DCM enable logic. Now, if you go inside the controller, that means if you take this controller, inside this controller is this block, where this is your output voltage, this is your ADC converter. So, that means this process is here. Then we have this subtractor, which is nothing but here. Then we have this controller, which is here. Then this is our comparator, which is here, and followed by this is our latch circuit, which is nothing but our here. So, then it will generate the gate signal, and this is a complete this diagram. This is a diagram which is realized here. The whole diagram represents which will implement. That means input to this block is error voltage. This is the error voltage, that is your input, and it is coming from VN. There is one more input, which is a clock, that means your trigger signal. So, we need to sample with respect to a clock, and the output of this block is a control voltage, which is here. So, this is our control voltage, okay. So, that means Now, if you go to the actual MATLAB block, so this is what we have discussed in detail. So, we can digital controller, we can customize the controller parameter from outside. You can in fact use any tuning algorithm inside your Simulink block to update the parameter. So, whatever else you want, you can discuss, and we will discuss that using trigger clock you can make the sampling process customizable and you can adaptively vary during the runtime. Okay, and we have made some simulation case study. So, now if you want to do a load transient case study with a 20 ampere load step, I am just showing the scenario. So, this is the simulation result of a 20 ampere load step. Now, you can reduce, this is a proportional gain, all this block we have discussed. Now, if you want to make, instead of load transient, I want to make a reference transient. So, 0.05, just 0.5 volt reference transient, then you will see that now there will be a change in the reference voltage. Okay, so this is the reference transient. I have not yet discussed the digital control design, that is why I am just showing some, I have chosen some arbitrary value of the controller gain, but it is just to show that you can realize this controller by using MATLAB. And here we are incorporating delay. You can see the sampling time and the switching times are different. So, sampling is happening fast and then switching happening. So, you can customize this delay. Okay. The next part is that if we want to do a supply transient, that means we can do a supply transient minus 4 volt, let us say we can do a supply transient in voltage mode control. We have not considered any input voltage feed forward. So, you can do input voltage feed forward because the effect is quite significant. This is due to the nature of voltage mode control, and if we do an input voltage feed forward, then you can very easily nullify or reduce this effect due to the supply disturbance. Okay. So, that means we have discussed various case study, and now the model is ready. So, we can go for the design in the subsequent week. In the next week we will go for the design, modeling and design will come in the subsequent week. So, in summary, we have discussed custom MATLAB model development for overall digital voltage mode control implementation. Then we have also discussed MATLAB simulation case studies. Then we will go for digital current mode control in the next lecture, MATLAB model development. So, I want to finish it here. Thank you very much.